In this slide deck, I'm going to go through some database design topics. This is a little bit more of a generic database design slide deck. It's not as academic as perhaps some of the other videos, but when we talk about database design, we usually talk about two types of database design. There's logical design, which is where we think about our entities and how they're related, but without any regard to the database management system and the physical database management system and what its limitations are. We don't care about any of that stuff. We just want to show what these relationships are going to look like. And then in our physical design, we typically take that logical design and we adapt it to a particular technology, right? Typically a relational database management system, but it's typically how we gear these designs. But it could be a hierarchical file structure. It could be a NoSQL or some kind of data structure like JSON or XML or something like that, right? So there's other options out there, but typically we're talking about RDBMSs rather, and how we design for those. I've talked about this in other videos, but in logical design, we refer to them as entities and attributes. So entities all have relationships and they contain attributes that describe the entity. So those are the terms we'll talk about in logical design. But in physical design, we talk about tables, which is really an entity, right? So an entity manifests itself as a table. An attribute, which are things that describe an entity, are columns or fields in our database design. And then you can have rows and columns that that are actual instances of those records in a database. And then in the theoretical terminology, right? So in computer science, data science, we call tables relations. We call our column or field attributes, just like we do in a logical design. And then our records or rows we call tuples, right? So a relation is a collection of tuples, right? This all comes from mathematics, from matrices and things like that, if you're familiar with some of those concepts. So in an ER diagram, you typically have an entity, right? So it's a standard method for diagramming entities, relationships, and attributes. I get into much more detail in my ER diagramming videos, but it's basically a modeling technique. And there's also another technique, class diagramming in UML. So you could also learn a little bit about UML. UML is just an alternative to ER diagramming. I think if you're a programmer, if you're developing applications and you're thinking beyond just the database, you're going to be typically doing class diagrams. But when we're database designers, you're building structured systems, using the structured technique rather for procedural systems, we're going to be doing ER diagrams. And then you have process. So the process for doing an ER diagram is first you use some analysis to reveal all the nouns, right? All the person, places, or things, and we try to identify which ones the system has to remember. In other words, persistent, right? Which ones have to be persistent between runtimes in a system, and that's what's going to be a database. So you group them into common themes, which are going to be our entities, and then some of those nouns are going to be attributes that describe those entities as we look through those different nouns. And then some of them are special. They're primary keys, which are going to identify a particular entity, which, again, we've talked about this before. So as an example, in your entity diagram, you have your entity name, and then you've got a bunch of attributes, and one of them is going to be a primary key, and then you have a key type. And again, this is typical for database design, right? We use this format. So some of the entity types, you can have weak entities, lookup entities, linking entities, domain entities, right? So I talked about some of this stuff in my ER diagramming video, but basically, is it an entity that can stand alone? Does it require the existence of another entity? And what's the degree to which these entities have a relationship or an association? So as an example, let's say we had a library, right, which has books, right? So books have they have a title, a publisher, a year, and they might have a bunch of subjects, right? Books, a good primary key for a book would be something like the ISBN, right? It's a good natural key to identify a book. All books have an ISBN, so it's, well, almost all books, right? At least ones that are published after ISBNs came into existence, right? And then they also have an author, right? So we might have, a primary key for the author as an example. And we can reference that author from our book table. So we use a foreign key in the book table, and that would be our maybe author key, right? We reference that primary key as the foreign key. So the primary key, again, that's a natural key. It's not a surrogate key. However, this other one over here on the right, we made that up, so we call it a surrogate key, right? It's a value that we just, arbitrarily assign to an author. It's not something that they inherently already have. So then we have there's two notations to show the relationship, right? You have the arrowhead, which shows that the book owns the author, right? In class diagrams, they call this navigation visibility, right? Um, and then you have your crow's foot notation. So an author can have many books, and a book can have many authors, as an example, and that's the crow's foot notation. So this is how we read it, right? By the way, the O is 0, the single line is a 1, and the crow's foot is many. So when we read this relationship, we say that a book can have one and only one author, and then an author has one or more books, right? So in many cases, the cardinality is determined from a business rule, right? So how many books can an author have? That might be a business rule. If this were a library database, if we had patron on here, a patron can only have maybe 5 books, right? So that cardinality, and really we call that multiplicity when we show the actual number, right, of how many things something can have. And again, that's something more from class diagrams. But then we might have repeating fields, right? So here we see subject 1, subject 2, subject 3. It's a repeating field. Typically, we don't want those to be in a database table, so we're going to create a separate table for that. And then we're going to get rid of those. So in this case, we might say that a book can have anywhere from 1 to 3 subjects, and a subject can have 0 or can appear in 0 or many books, right? And that's pretty typical for a library, right? In libraries, well, not anymore, but in the old days when we had card catalogs, you would only your taxonomy would limit every book to 3 subjects. That way you didn't have thousands of cards for every book in the card catalog, right? Because you had to have a card in the card catalog for the author, you had to have one for the title of the book, and then you also had to have your 3 subject cards, right? That way people could find the book by subject, by author, or by title. So that means every book would have 5 cards in the card catalog, unless you had multiple card catalogs. So if we didn't limit the number of subjects, we would have a lot of cards. So it's just a vestige of the old days with card catalogs, which many of you probably never even used one, right? So this is not really normalized yet, right? So we haven't done any normalization. We're going to talk about that in another video, or you may have watched my other videos that talk about normalization already, but I've got a couple different videos that discuss that. So you have different types of relationships, right? We have a one-to-one relationship where for each record in the primary key table, there is no more than one related record in the foreign key table. So for example, they're very rarely used, right? We don't see them very much, but one use for these is to obviate the need for null values in our database. Nulls are bad. Nulls are going to ruin your day. So we want to try to avoid having nulls. Nulls doesn't mean 0 or it literally means nothing, right? Null means nothing. There's just an absence of data. And the problem with nulls is that since they don't really mean 0, right? If you try to add, if you try to order by nulls, if you try to do certain operations and there's a null value in the record set, the database doesn't know what to do, and it can cause some, it might manifest itself as sums that don't total. They come out to null instead of an actual value. It could be that when you try to order a column, it doesn't actually work, right? So there's a couple different reasons not to have nulls, but let's look at an example, right? So let's say I've got media, right? Think about a library. Libraries don't have just books, right? They have CDs, they have, movies, they have magazines, right? They've got lots of different types of media. So let's say I only had one table called media. So the first record in this table is a book. It has a publisher and an ISBN. The second one is a movie, so it's got a format and a release date, right? Books don't really have a release date. They just have a publisher and ISBN. And then we have a magazine, which has an issue and a volume, but that doesn't really apply to the other records. So all those black boxes you see are nulls. And I just said we want to try to avoid nulls. So how do we fix this so we don't have a lot of nulls? Well, the first thing we need to do is get rid of, we have to remove these, the values from our media table that are grouped together, right? So groups of values that could be null that are really transitively dependent on, have a partial dependency on something else. We're going to remove that and create another table. So for example, the video, we'll create a video table that shows the format and release date. And then we'll create a book table for the publisher and the ISBN. And then we'll create a magazine table for the issue and the volume, because only magazines have an issue and a volume. Sorry, I I actually just accidentally closed my PowerPoint. Give me 1 second. All right, sorry about that. We're back. So now we have our original media table, which just has the title because they all have titles. But then all the other stuff, right? We made our own tables. Now, if you think about this, this is really what that media table was. Um, Whoever created that diagram should have recognized that it was a super type and subtype relationship, right? So really the super type is media and the subtypes are video, book, and magazine. And if you look at some of my other videos, I talk about how to resolve super type and subtype relationships into relations. And this is the exact same process, but we're basically taking a step back because our ER diagram for some reason doesn't show that that association relationship. So instead, we have to kind of break it apart as we go through this design process. But obviously, we would want to in our ER model, we would want to identify that if we can. So what would this look like? It would basically now our table our media table has three records, these three titles. And then our video table has the video in it, the book table has the book in it, and the magazine has the magazine in it, right? There is another step here, though. We have to add the foreign keys, right? So we have our media. Our media can be a video, a book, or a magazine, and it's going to be a one-to-one relationship for each one of these because of the type of association this is, which, again, you can think back to one of my videos about how to resolve supertype and subtype associations. But again, we have to add our foreign keys here for this really to work. So we'd have to add a foreign key into video, book, and magazine when we do our final database design. Another reason that we could do a one-to-one that I didn't talk about in my other videos is security, right? So, for example, when you look at an employee record, the last name and the first name are pretty much public, but the social security number and the salary should probably be kept private, right? So there should be extra security on those fields. So maybe we want to pull those out of the employee table and create a new table for the employee that only has those two fields and make it a one-to-one relationship. That way, the employee payroll table, we can have special permissions that only authorized people can see that table, whereas the other table can be exposed publicly. Now, there are ways that you could secure just the individual columns, but this would be a little bit simpler and a little bit more efficient to do it this way. Also, it's global, right? Because almost every database engine would be able to support this. You don't have to have any special features to support this. So again, security is another reason that we might do that. So a one-to-many relationship. This is the most common relationship that we should be seeing in our ER diagrams. So for each record in the parent, there can be 0 to many records in the child. So this is what it looks like. When we see that, we always, oh, by the way, yeah, so this is the cross relationship error is if it goes both ways, right? If we can have a one-to-many and then on going one way and then a one-to-many going the other way, we can't add a record to one without adding a record to the other, and then we get a cross relationship error. So that's something certainly that we want to avoid. And this is most likely, this is because it's really a many-to-many relationship, right? So if it's a many-to-many relationship, we have to add an association table between these two to manage that association, that many-to-many association. So in this case, an employee has many departments and a department has many employees. There probably needs to be a table in the middle because we wouldn't be able to we would have this cross relationship error as we tried to add records. I can't add a department because I have to have employees, and I can't add an employee because they have to have a department, right? So we need an association table in order to handle this. So to handle a many-to-many relationship, as we just said with employee and department, we're going to add some kind of an association between the two. And again, I'll talk about that more with the normalization. So our naming convention should be consistent, right? So entities and tables should typically be named with single nouns. We don't call them books. We don't call it authors. We just call it book and author and employee and so forth. The attribute names all have to be unique across the entire database. You can prefix with the table name if you want to make sure it's unique. That's certainly one way you could do it. Primary keys should have consistent names. For example, employee key is the primary key for employee, right? I use the same format, the same syntax to name all my primary keys. It just makes it a little bit easier. And foreign keys would retain the same attribute name as the primary key to which it references, and that's important. Like you could have primary keys that are a completely different name that reference the primary key in another table, but then it gets confusing, right? So it's a good idea to use the same key name for a foreign key that it is in the primary key table. It just makes it easier to identify those. Now, of course, in the database management system, it doesn't care what you call these, right? You still have to define that foreign key relationship. But certain queries work a little bit easier when you use the same naming convention. You can do natural joins, for example, in Oracle and MySQL without having to, explicitly define what the foreign keys are in your query. And that works when either A, the database management system knows the relationships, or B, if you use the same name for the primary and the foreign key. One other note here is it's typical to try to use camel case. If you never heard of that, camel case, that's if you look at employee key, right? The first letter of every word in the attribute is going to be uppercase. Could you have spaces in attribute names and table names and so forth? Yeah, I mean, in theory, many database engines will support that, but it's generally best practice not to do that. So generally, we don't want to use spaces and special characters. We just want to jam all the words together, use that camel case. You could use underscores if you want, but again, that's a special character. Um, you could have compatibility issues with different database engines if you do that. One thing that people will tell me is, Brian, I don't care about compatibility issues. I'm designing my database for Microsoft SQL Server or for MySQL or for Oracle. And, if another database engine doesn't support the syntax, what do I care, right? I've had people tell me that. And my answer to that is, that's not always going to be the case, right? I may be building my database in Oracle and it may be being deployed in Oracle, but maybe somebody in Microsoft SQL Server is going to create a link to that database because there is information that their application needs. And if I do that, if that database has an issue with some of the formatting, it's going to cause problems, right? It's going to ruin your day. So it just makes things easier for everyone if you just try to keep things simple and try to use the industry standards for your naming conventions, and try to follow these basic rules. So that's just my basic overview for database design. Again, this is kind of a simplified version of my database design presentation, and I have another one for normalization that you might want to review as well.